Welcome to The Explainer. Today we're diving into something that, well, looks like a basic math lesson on the surface, but is actually a total masterclass in cognitive development. We're breaking down Chapter 3, Fun with Numbers, from our source material. We aren't just talking about counting here. We're going to look at the exact structured way this chapter literally wires a young brain for complex mathematical reasoning. Let's get right into it. Think back for a second. Do you remember how you first learned to visualize numbers? For a lot of us, it was just this blur of flashcards and rote memorization, just repeating sequences until they finally stuck. But what if there was a way to deliberately move a child from physically touching objects to visualizing abstract mathematical patterns? Well, the material we're looking at today does exactly that. It completely trades in that rote memorization for a super dynamic number sense. Here's our roadmap for today. We'll be hitting 4 main zones: counting with the Ginladi, dynamic number lines, the 100-grid spatial window, and finally, visual math and games. Okay, starting with part 1, counting with the Ginladi, the physical anchor. So this brilliant little tool is called a Ginladi string. What's absolutely fascinating here is how it acts as a tangible physical anchor. The chapter doesn't just ask a kid to magically imagine the number 38 or 98. No, it asks them to physically count the beads, which are grouped in alternating colors, and place blank cards at very specific points along the string, like 38, 44, 58, and 98. It takes the totally abstract concept of a number and grounds it into a physical distance that they can actually see and touch. It's brilliant. Moving right along to part 2, dynamic number lines, bringing numbers to life. Now, we usually think of number lines as rigid, straight rulers, right? But the source material evolves that straight line into this curving, snaking path, winding its way from 49 all the way up to 100. By curving the line, it essentially forces the brain to visualize higher numbers with way more spatial flexibility. It's not just a boring, straight march to the right anymore. The numbers are flowing. It makes the whole visualization process so much more adaptable. And movement means characters. The text brings in these fun characters, like a butterfly and a jumping frog, to teach skip-counting narratives. It asks the learner to imagine, hey, if a frog starts at 10 and jumps in tens, will it land on the number 100? Or if you start at 5 and count in fives, are you going to land on 40? By personifying these jumps, skip-counting transforms from this boring, repetitive drill into a physical narrative. You're not just reciting numbers, you're literally following a frog down a path. But then they throw a major curveball. We start with forward skips, 40, 45, 50. Easy enough. But then the chapter suddenly shifts to backward skips, 100, 90, 80, or even counting backward by 3s and 5s, like 40, 37, 34. The cognitive shift here is absolutely massive. Think about it. Counting forward relies on natural momentum. Counting backward? That requires the brain to actively subtract and hold the whole sequence in its working memory. It's a fantastic mental workout. To truly cement this skill, the chapter introduces word problems. And get this, without giving the kids a visual grid to trace. It asks things like, if Mala is counting backward from 20, how many steps will it take to reach 0? Or, if Viraj is counting backward in 2s from 20, how many steps for him? Just pause and think about the mental gymnastics it takes to solve those backward-counting logic puzzles in your head without using paper. A kid has to visualize the jump, count the jumps, and track the declining numbers all at the exact same time. All right, moving into part 3, the 100-grid spatial window, escaping the line. So here, the source introduces a classic 10 by 10 grid, laying out the numbers 1 through 100. But it's what they actually do with it that's so clever. The chapter asks students to look at numbers aligned diagonally. This creates brand new, almost hidden visual sequences like 1, 12, 23. Suddenly, kids get this amazing aha moment that adding 11 isn't just a math equation. It's a physical diagonal line cutting right across a square. Numbers literally start to have a geographic location. And that leads us to one of the most ingenious tools in the entire chapter, the number window. It's a spatial tool placed over a grid to find adjacent values. The text asks, okay, if the center of the window is placed on 28, what number is on top? What is below? What's to the left? And what's to the right? Why this matters is absolutely profound. By simply asking what is above or to the left of a number, the book invisibly teaches addition and subtraction by 1 and by 10 based entirely on visual location. Moving left is -1. Moving up is -10. I mean, it's essentially spatial algebra. Finally, we're at part 4, visual math and games, abstract reasoning. Let's check out a game the text calls Dice Bingo. The rules are pretty simple. First, you make a 3x4 grid. Next, you fill the boxes with any numbers from 2 to 12. And yeah, you can repeat numbers. Then, you throw 2 dice, find the sum, and cross it off. First one to cross off their whole board wins. Now, on the surface, it's just a fun little game. But secretly, it is drilling rapid-fire mental addition. And even more importantly, it subconsciously introduces the concept of probability. Kids are going to figure out real quick that filling their board with 7s and 6s is a way better strategy than filling it with 2s and 12s, simply because those sums roll way more often. The chapter wraps up with an exercise in exploring patterns. Sequence A is 1, 4, 9. Sequence B is 5, 8. Sequence C is 1, 3, 6. The source pairs these numbers alongside growing geometric block shapes, asking the learner to extend the pattern. Associating these growing geometric shapes with numerical sequences is just incredible. Sequence A, for example, represents perfect squares, 1 by 1, 2 by 2, 3 by 3. It is literally building the exact foundational logic required for future algebra and calculus, totally disguised as a simple block-building puzzle. Which brings us to a question I want to leave you with today. Are we completely underestimating the complex cognitive journey hidden inside early childhood math games? We've just seen how this chapter deliberately moves a learner from touching physical beads, to visualizing skipping frogs, to mapping numbers on a 2D grid, all the way to predicting algebraic patterns. These specific tools build a deep, intuitive mathematical sense that rote memorization just cannot touch. I really hope this breakdown gave you a whole new appreciation for the brilliant structure behind foundational education. Thanks for joining me on this explainer, and definitely keep exploring the patterns around you.